Welcome SSP and Dell students. This is your new lesson for Markowitz Model. So we are going to have an overview of Markowitz Model for Financial Engineering 354. So we use Markowitz Model to optimize or to find the lowest risk for a return, right? We have a return, or we have a portfolio return, like we have our own desired portfolio return, and we are trying to find so we have our return, we have our own expected portfolio return, and we are trying to find the minimum risk. We are trying to find the minimum risk. So Markowitz model will help us to find the minimum risk for a specific portfolio return. So how do we do this? So first, we have spoken that risk can be measured with this equation, the sum. This looks ugly. It's gonna be the sum of I, j, with I, with j, sigma I and j, right? So we have explained that this is gonna be your formula for risk. So we are trying to minimize this risk. This is what we are trying to minimize. We are trying to minimize this. This is what we are trying to minimize. We are trying to minimize this, right? So before we minimize it, we have to understand that there are constraints. There are constraints that you need to take into consideration. Constraints. And what are these constraints? So your first constraint is that the returns of your portfolio, there's going to be the returns of your portfolio. This is going to be a constraint, the returns of your portfolio. The other constraint is going to be the weight of your portfolio. So the weight should actually be equals to 1, right? So anyway, when you have something like this, you are going to find your Lagrange equation, which you do in multivariate calculus. I don't know if it's, yeah, I think it's only in multivariate calculus where you're gonna have something like this. So your Lagrange is gonna be something like this. It's gonna be your I, your j, weight of I, weight of j, sigma I, this minus, and then you're gonna have lambda, and then your constraints, and then you're gonna say the sum of I, weight of asset I, and return, and the returns of the portfolio, right? Minus mu, the sum of I, weight I, minus 1, right? So this is your Lagrange equation. So you are going to optimize this, right? How will you optimize this? You're gonna find the first derivative, or this you say is the partial derivative in terms of wi, and then you're gonna equate it for, again, I'm like, you're gonna equate it to 0. This happens for all the i's, right? For weight I equals to 1, I equals to 2, I equals to 3, up to I equals to n. So you could have more than 3 or 4 assets, right? And then again, you're gonna find the partial derivative of mu of the Lagrange equals to 0, and then again you're gonna find the partial derivative of mu of the Lagrange equation, and then equals to 0. And then what you will have as an answer from this thing will give you an answer, and your answer will look like this. And I'm gonna write it in matrix form because it's much easier that way. So you're gonna have sigma 1 1, which is gonna be your covariance of 1 1 1 2 up to 1n, right? minus the return of asset 1 minus 1. This happen up until you have sigma n1, sigma n2, up to a point where you have sigma nn minus the return of asset n minus 1. And then you're gonna have the returns of 1, returns of 2, up to the returns of n, right? 0, 0, 1, 1, 1, 0, 0. All this multiplied by their weight. So so you're gonna have weight of 1 up until you have weight of n, and then your lambda and your mu. All this equals to 0 up to 0. The returns of your portfolio 1, and then you're gonna reduce this equation. So this is basically can be written as ax equals to b. So you are going to reduce a. You are going to reduce a to find your answer, and that answer will give you the minimum variance of your portfolio. So you're gonna find the minimum variance of your portfolio for your given return. So that is one thing, right? So there is a problem. There is a slight problem with this. Sometimes they don't tell you what the returns should be. I mean, like the returns of your portfolio. What do you do in such a case when the returns of your portfolio is not given? So you are gonna go back to your Lagrange equation again. So the first derivative of your Lagrange equation equals to 1, right? And that and that thing was gonna be equals to what? It's gonna be equals to j, weight of j, sigma I j minus lambda ri minus mu equals to 0, right? So equals to 0 for all i's, right? And then you're gonna say let alpha, let this equals to 0 and mu equals to 1, right? Let lambda be equals to 0 and mu equals to 1. And then what you will have as an answer, right? So what you will have as an answer, it's gonna be something like this. This is what you will have as an answer. I am not gonna do these things step by step. So you're gonna have variance 1, 1, 1, 2, up to 1n, all the way to n1, sigma n2, sigma nn. The weight of 1 up until the weight of n equals to your ones, and then you're gonna have your ones there all the way. You're gonna have 1, 1, 1 up to 1, and then again you are going to you will have a x equals to b, and then you reduce x. You reduce a, you're gonna reduce the rows of a, right? And then find your weight. One thing about this weight is that these weights are not normalized. The weights you're gonna find are not normalized. What do I mean by they are not normalized? It simply means that they are not necessarily going to be equals to 1. The sum of all your weights of so the weight of j, they are not necessarily going to be equals to 1. So you will have to normalize them by doing this. You will have to say y0, let y0 be equals to this. They're gonna be equals to the sum of all the weight, right? And then after you have found all the sum, so you're gonna say the sum of I is gonna be equals to the weights that you find. I'm gonna use j, the weight that you have found over weight of 0. So this will be a normalized weight. This will be normalized, and the sum of all the vj's is gonna be equals to 1. So this simply means that it is normalized, right? So there is another problem. So this one was actually looking at the minimum variance. I forgot to mention that. So this actually looks at the minimum variance. It looks at the minimum variance, right? This is what you were looking at, only at the minimum variance. This is the portfolio that we were looking at. This is the portfolio we were looking at. We often call it I use red. We will often call it by minimum variance portfolio. So when you try to find the minimum variance portfolio, you're going to say lambda equals to 0, mu equals to 1, right? But then what if they ask you to find any other portfolio that lies on the efficient frontier, right? If that's the case, what you will do, any other efficient portfolio. So what you will do is that you are going to let mu, like lambda equals to 1 and mu equals to 0, and then you're going to solve. So again, I'm not going to do the math behind that. So you are going to have your covariance matrix, times your weight 1 up to weight n. It's going to be equals to the returns of asset 1 up to the returns of asset n. And then again, you have your ax equals to b. You reduce your x, like you reduce your a, you reduce the rows of a to find your answer. And then again, still, the weight that you are going to find, they are not going to be normalized. They are not normalized, not necessarily normalized. So again, to normalize them, you let mu 0, it's going to be the sum of all the weight, and then to find the weight, you are going to say weight of j over weight of 0. So this will be your normalized weight. So if you have any question, so all of you who are under Dell and SPP, like SSP, you can WhatsApp me, and then, or we can discuss this in our next session. So anyway, this is where I'm going to end with the video. Thank you.